This is an AQA A-level chemistry topic. It's from year 13 and we're looking at structure determination. This is part 2 of this series. In part 1 we looked at carbon 13 NMR, and in this one we start to look at hydrogen NMR. So going to recommend, as always, that you pause, have a go at the activities for yourselves and then see how you've done. That way you get to know where you need to develop your understanding and where things are going well. So in this video, we're going to introduce hydrogen NMR spectra, and we are going to describe what that can tell us. And it's actually a huge amount more information than we get from carbon 13. And we're going to explain what an integration trace shows, which is part of that. Now, there are some similarities. You'll see there's a data table on the right hand side. That's also provided in the exam, just like the carbon 13. You've got to be confident using it. And I want you to take a look at each one of them has got an H in bold. When we talk about a hydrogen environment, we're talking about a hydrogen in the environment where it's bold in that species. So we'll get to that in a few minutes, but let's have a think about some of the similarities. Because it says here that we are using tetramethylsilane as our reference, and that's exactly the same as we use in carbon 13. What does it look like? What are its advantages? Well, it looks like this. We've got a silicon in the centre with 4 CH3s around it. And it does have numerous advantages. First of all, there are 12 hydrogens in the same environment. That means that there's going to be one very strong single peak. It will also always be upfield of the species that we're analysing. So that essentially becomes naught on our NMR. It becomes our reference that all things are measured against. It's also, and this can be worth marks in the exam, it's inert. Now that means that we're not at any risk from it. It won't react with what we are reacting. It's non-toxic, which makes it safe to use in terms of our own safety within the lab, and it's volatile. And that's an important one because actually it can be very easily removed once the analysis is done. It will simply vaporize away. Now, we can also look at the fact, going back to this first point, that reinforces what I said actually before those three. The high shielding means the peak is upfield. It will be to the right of all of the others in the sample. So it's set as 0. So let's go on to do some analysis. And we've got environments. We looked at carbon environments. We're now doing the same for hydrogen. So have a read through, have a think about this question. How many environments are there? So I've highlighted one H there, and because that H is coming off a particular carbon, it's fair to say that every hydrogen coming off the same carbon has an identical environment. But also, if I look at the H, I take one of those H's, it's connected to a CH2, CH3. Well, actually, that's true of the 3 on the other side as well. So there's only one hydrogen environment here. We've got one. Couple more examples for you to try. So in the first one, we already know that the 3 H's on the same carbon are all in the same environment. We definitely have a different environment here. There's only 2 hydrogens on it, and these hydrogens are on a carbon bonded to an O. These hydrogens aren't. And we also have an H in an OH. That's definitely a different environment. So what we have here is a total of 3 environments. And if we take a look at propane, I've got my 3 in the same environment here. Actually, the 3 at the other end are an identical environment. We've got symmetry within this molecule. And we've got those 2 in the middle that provide the second environment. There are 2 environments in this example. And now let's take a look at this ester. Well, my 3 on the left-hand side are definitely, they're on the same carbon, so they're in the same environment. If I go to the other end, I've got another CH3, but this hydrogen is bonded to a carbon bonded to a C double bond O, whereas this hydrogen is bonded to a carbon bonded to a CH2. The environments are different. I then have a third environment here. We have 3 hydrogen environments in total. So now let's move this on a little bit, and we're going to look at the chemical shift. Once again, you've got experience of this with carbon 13. Here we have got chemical shift values. These are the regions on the NMR where you will find the peaks. So let's have a think about what peaks we would see, how many peaks we would see. Have a think about these and then we'll review. So in the first instance, ethane is CH3CH3. I'm going to draw that out in full there actually, and we can see that I've got this hydrogen, and we know that all of these are actually in the same environment. Now, which H does that tally with in the table over here? Well, it's an H on a CH3 with an extended chain beyond it. So this is RCH3. And what that means is that we will get one peak on ethane, and it will be somewhere between 0.7 and 1.2. Let's move on now to ethanol. Well, let's start with the yellow peak. I've got my H here bonded directly to an O. Well, there's only one where that really happens, and that's the ROH, which is up here. And that means that we're going to get a peak because of this hydrogen environment somewhere between 0.5 and 5. That's actually not incredibly helpful because it could be one of many things. But it is still useful. Certainly if we know we have an alcohol, we can start to narrow down what peaks are causing what. Let's move on though, because we've also got these three at the end. Well, that's another RCH3. That's going to be somewhere between 0.7 and 1.2. And we still have a third environment. We have H's, an H bonded to a C, and in this case, it's bonded to a C that's bonded to an O, that's then going off to be connected to something else. That means that we're going to get a peak between 3.1 and 3.9. So we know how many peaks there will be, and we know a fairly good approximation of where on the spectrum we would find them. So let's go on to propane. On propane, we have got all of these which are in the same environment. That's our CH3. That's another RCH3. This is really common. We're going to get a peak between 0.7 and 1.2. For the one in the middle, we're actually looking at R2CH2. It's a hydrogen on a carbon with another hydrogen and two R groups coming from it. So we're going to get a peak here between 1.2 and 1.4. Finally, ethyl ethanoate. If we start by looking at the yellow hydrogens here, well, they are bonded to a C double bond O. So we're actually looking at a peak in the region of 2.1 to 2.6. I move along the sample, the structure, and I get to these three H's, and we're back to the old familiar. That's an RCH3, so we've got a peak between 0.7 and 1.2. We've still got these. We've got the two H's. Now, what does that most look like? You're routing through all of the examples on the right hand side, and what we can see is this is an H, which is bonded to a C, which is bonded to an O, which is bonded to a C double bond O. That means that we're going to get a peak between 3.7 and 4.1. So as we go through all of these, we are seeing just how much information we can already get. We know how many peaks we would expect, and we know where those peaks would be. So let's take it a step further and let's look at integration traces. Now, we don't do this with carbon-13. This is new to hydrogen or proton NMR. And it says, look back at the example, peaks of two environments are different sizes. I've got three H's in one environment. That's giving me a peak around 3 times bigger than the one where there's one hydrogen environment. You can see the 3 hydrogens and the 1 hydrogen in a 3:1 ratio. Now, it's not actually the height of the peak, it's the area beneath the peak, which is very difficult to measure, so we use integration traces. So the area under the peak is directly proportional to the number of hydrogens in that environment. The calculation will be done for you, and you will be given integration trace values, which is essentially the ratio of hydrogens in the environment. So what would the ratios be in the 4 examples that we've seen? Well, let's start with ethane. Ethane's only got one peak, so it's not really a ratio, it's one peak. But if I move on to ethanol, if I draw that out, remember that we have got 3 peaks. We've got 3 hydrogens in one environment, 2 in another, and 1 in another. So the integration trace values would be in the ratio 3 to 2 to 1. Now, they might not be given as 3 to 2 to 1. They might give you 0.64, or sorry, 0.6, 0.4, 0.2. Or 0.09, 0.06, 0.03. It's the ratio that's key. Let's move on to propane, where we have got 2 different environments. We've got 6 in one environment, we've got 2 in another. And that means that we've got a 6 to 4 ratio, which we can simplify to a 3 to 2 ratio. And finally, we can take a look at ethyl ethanoate, where we've got 3 peaks, and the ratio, as you can see from the colour coding, is 3 to 2 to 3. So that takes us to the end of this second video. In part 3, we develop Proton NMR further and look at some past paper practice. Thank you for listening, and goodbye.